So far with the density matrix, we've introduced the idea of mixed states, represented them using the density matrix, and effectively rewritten Schrödinger's equation with this new notation. Remember, the mixed states are ones in which we only know with some presumed classical probabilities which of several different pure quantum mechanical states actually describes our system. Since a pure state is just a special case of a mixed state, this formalism can also be used with pure states. So it can be thought of first as just a new notation. The density matrix can, however, allow us to handle other aspects of the interaction of our system with the rest of the world in a simplified way, but one that is quite convenient and effective, and that is where the real power of the density matrix lies. We can introduce this aspect of the density matrix by considering one simple but directly useful example. We'll look at how light interacts with a two-level system. We can think of this two-level system as being a simple model of an atom. Now, we've already looked at this kind of interaction using time-dependent perturbation theory. That approach was quite successful, but it did leave us with a problem. The resulting optical absorption line was infinitely sharp in frequency, and that's obviously unphysical. With the density matrix, we can approach this problem without using perturbation theory, though that change of approach would not in itself get rid of the difficulty of this infinitely sharp absorption line. However, the density matrix rather conveniently allows us to do something else. We can introduce the interactions with the rest of the world using something called a relaxation time approximation. That approach is very powerful and effective, and it's an approach we can really take only with the density matrix rather than just the original Schrödinger equation. So let's start on our example of the interaction of light with a two-level system and see how this works.
Let's take a two-level system of some kind. So here's level 1 and level 2. They could be electron states, for example. And they'll have energies E1 and E2. And we will have associated eigenfunctions for these states of psi1 and psi2, respectively. Presume that this system, for example, it might be an atom, is much smaller than an optical wavelength. So an incident optical field, E, a vector E here, will be uniform across the system. So here's our electric field, and whatever it is, it will be approximately the same everywhere over this system. And we'll take this field to be polarized in the z direction, so we'll call this the z direction. And we'll give it magnitude, of course, E. We're just going to treat the interaction with the electric field semi-classically here. We could use other approaches such as annihilation and creation operators, but for simplicity we'll just use the semi-classical version for the moment here. And we'll take an electric dipole interaction, which we've seen many times before, between the light and the electron in the system, so that the energy change on displacing by an amount z is simply the electronic charge times the electric field times z. Hence, we can take the semi-classical perturbing Hamiltonian as just this form. So this is the form we've seen before, and formally now we're going to introduce a new notation, though no change in the physics, where mu here, which we now explicitly write with an operator hat on it, is what we will call the electric dipole operator. And it has matrix elements that we could write like this. So mu is basically minus Ez, and the matrix elements are therefore minus Ez inside this form here. So the matrix elements of our perturbing Hamiltonian, this is our perturbing Hamiltonian, then become simply minus E times mu mn. We choose the states psi1 and psi2 to have a definite parity in the z direction for simplicity. This is often the case with atomic states anyway. So with our definition of mu mn the matrix elements of the dipole operator, then by definition then, because these are chosen to have definite parity, for m and n being the same, this whole form here, this matrix element, will vanish. So mu11 and mu22 are 0. And hence, with our definition that the perturbing Hamiltonian and its matrix elements, mn here, are in this form, then the matrix elements 1, 1 and 2, 2 of the perturbing Hamiltonian will also be 0. We're free to choose the relative phase of these two wave functions in our definition such that mu12 becomes a real number, which is just more convenient for us, so that we have mu12 is equal to mu21, and we'll just call that this number mu d. So a dipole matrix element magnitude here. Hence, our dipole operator, mu, can be written in this matrix form. Because the wave functions psi1 and psi2 had definite parities, we deduced that the elements on the diagonal here of the dipole operator are just 0, and because we chose the relative phase of these two eigenfunctions in a particular way, then these are just equal real numbers. So the perturbing Hamiltonian then is just minus e times this matrix, which gives us this form here. The unperturbed Hamiltonian H0 is just a 2 by 2 diagonal matrix on this basis because we chose these basis functions, psi1 and psi2, to be eigenstates of the unperturbed Hamiltonian. So the unperturbed Hamiltonian then as a matrix is just a diagonal one with E1 and E2 as the diagonal elements. So adding it onto the perturbing Hamiltonian, this is what we get from the unperturbed Hamiltonian, and this is what we get from the perturbing Hamiltonian to give this total Hamiltonian here. The density matrix here, because we're just working with these two functions, psi1 and psi2, is also a 2 by 2 matrix. And in general, we can write it simply in this form. We haven't done anything here other than labeling rather obviously these elements of this 2 by 2 matrix.
The dipole induced in this system is important for two different reasons. First, as above, we see that it's closely related to the perturbing Hamiltonian. Second, it represents the response of the system to the electric field. In this case, that response is essentially the polarization of the system by the field. And the relation between polarization and the electric field gives the electric susceptibilities or dielectric constants that we typically use to describe the optical properties of materials. So here we want the expectation value or ensemble average value of the dipole or dipole moment, which is the microscopic physics that's telling us how the system is responding to the applied electric field.
We have not yet defined the system's state, but we can already use this relation that we deduced before for the density matrix, that the ensemble average value we would get for the expectation value of some property associated with this operator A would just be the trace of the density matrix times that operator. So we can use this relation to write that the ensemble average value we will get for the expectation value of the electric dipole operator here will just be the trace of the density matrix times this electric dipole operator. Well, using this relation for mu and for rho, just definitions in that case, we can multiply this out. So rho times mu is simply the product of these two matrices here. And for example, the element up here is just the result of multiplying this first row by this first column. So all that's left is mu d times rho 1, 2, and that's what we see here, for example. Hence, the expectation value of the electric dipole operator in an ensemble average is the sum of the diagonal elements of this matrix here, this product rho mu, which is of course just ρ12 mu d plus ρ21 mu d, or equivalently mu d times ρ12 plus ρ21.
So, now we've related the ensemble average expectation value of the dipole of the system to the density matrix. Remember that the density matrix is going to be representing the mixed state of the system as well as that can be represented. The dipole of the system induced by our applied optical electric field is going to allow us to calculate whatever optical properties we want, such as optical absorption or refractive index. So the next stage is to deduce just what the density matrix is once we have applied our oscillating electric field from our instant light.